Swayam Prabha. Digital India. Educated India.
Okay. So let's go to more complicated ones. Edit distance. What is edit distance?
How many changes we have to make in the word to get another?
So edit distance is something that you see between strings, right? You've seen between strings, right? And a lot of the times it is also known as something called dynamic time warping, right? So if you read some time series literature, if you happen to come upon time series papers, you will see them call this dynamic time warping. It's really edit distance. Okay. What does it mean? It means that you want to go from one string to another. Let's say you want to go from this string kitten to this string kitten to this string, right? You want to measure the distance between these. So you are saying, let me count the number of changes that are needed to make from this string to this string, from kitten to sitting, right? Here we have sort of changed one letter, then we have changed another letter, then we have added one letter. So three, right? And we could say that the edit distance is 3. We could also do it more complicated way. We could define the cost of each change specifically. We could say that, really the cost of adding one letter is this, cost of deleting one letter is this, cost and so on, right? And we could define the cost of deleting and adding individual letters. Maybe A is easier to add because maybe there's a typo. I mean, people do typos in A, but maybe Z is sort of not very easy to add or delete, okay? So this is also a metric. Dare I ask, why is this a metric? Why does this obey triangle inequality? Other two are fairly easy to me, trivial to me. Why does this obey triangle inequality? Why?
If we make changes from word,
Sum of so the answer that is coming is sum of any two. No, what sides? So there's no question of collision. Okay, I think I'm missing something. There's no so when I write this here, what are x, y in this case? In this case, x, y are strings. So these are strings here. There's no geometrical representation. These are strings, right? As in, x could be the string A, B, C, D. Y could be the string kitten. Z is the string sitting, right? And D is the edit distance between them. Defined as going from x to y, how many changes do you need to do? So there's no geometry here. Absolutely no geometry, actually. But still, this is true. This is why it's important to think about it in a little bit abstract sense. Why is this true?
then if you need 5 changes from going from word A to word B and 5 more to go to word C, then if we directly go to word C, we still need to go to the first 5 changes.
Good point. Let me repeat the answer. So what is dxy really telling me? Dxy is really telling me that you need, let's say, 5 changes to go from x to y. dyz is telling me dyz equal to 3 means that you need to make 3 changes to go from y to z. So this is giving me a path to go from x to z already by going through y. That I make 5 changes to y to go from x to y, I make another 3 changes to go from y to z, and therefore I can make 8 changes to go from x to z. Maybe there is a shorter path, but certainly this is one path. So therefore, the shortest sort of number of changes I need to go from x to z can only be at most the length of this path, right? Because I might or might not go through the shortest path from x to z, might or might not go through the string y. Sorry? D actually, so the definition of D is that going from one string to another, what is the shortest number of changes you need to do? So in that sense, it's the shortest path through this.
If you consider it to be shortest path, then there can be a shorter route, right?
There can be a shorter route, which is why this is greater than or equal to. Should it be less than equal to, greater than equal to? Greater than equal to. Because this is on the right hand side is saying what is the shortest number of changes to go from x to z. On the left-hand side, I'm showing you one. So think of this as follows. This is.
So same is true for the x comma 1.
So this is one path. This is one path. But there's potentially one path. Same is true for dx comma y. Yeah, of course. See, I mean, x, y, z are just arbitrary symbols here. I could have just interchanged the symbols. Okay? So this is a metric. You guys have proved it. However, it is not easy to calculate it even for pairs, right? Because you did it, dynamic programming and so on, I'm sure you've done. So even if the strings are of length n, right, calculating even the distance between them takes n square. Right? And we know that you cannot really do much better. So it's not just that we teach you a stupid algorithm in your class and then people are using a faster one, right? People have been breaking their heads. It's just not possible. I mean, people have proven that it's just not possible to do a better algorithm. So while this is an important notion of distance, we don't really use it that much in clustering. This is another fun distance. I really like it. This is called Jacquard distance. Okay? When is it defined? It's defined when the objects are sets. What is the definition of this distance? Let me draw them. This is a Venn diagram. So the objects A and B are sets. So we define something called the Jacquard coefficient of AB to be A intersection B, A union B. So the Jacquard distance between AB is 1 minus Jacquard coefficient of AB. Is the definition clear? So the Jacquard coefficient of AB is the size of the intersection divided by the size of the union. Okay? And the Jacquard distance between them is 1 minus Jacquard coefficient. Okay. Now let us go through again our motions. This is non-negative. It's 1 minus. But Jacquard coefficient is between 0 and 1 because size of the intersection is always 1. Okay, not negative. Symmetric and so on, that's easy. Triangle inequality. Okay? So triangle inequality is not easy to prove. Very strangely. This is a fun exercise. In fact, we'll try to prove something in the afternoon today. However, as you can see, so two things. Okay, the triangle inequality, I mean, you can see here, I've pointed to a 1972 paper. Even that says the triangle inequality proof that was given before of this was surprisingly complicated. It took like, I've looked at the paper, I haven't gone through it, it took like five pages of solid mathematics for this simple definition. Even this paper, this Nature paper that sort of claims that it's an easy proof, it's a very dense 3-page proof, just to prove the triangle inequality. You will do this in afternoon today. Shouldn't take more than 10 minutes for you, right? But it's going to be a tricky proof. It's not going to be an easy proof, but we'll try to do this, okay? However, triangle inequality holds. What is yet another problem is this question of finding the average. So remember what we were saying, the average, that we are given n points, p1, p2, pn. You want to find the minimum, you want to find x such that argmin x I equal to 1 to n. Basically, you want to find some kind of center, right? Again, here remember, the PIs are the sets, right? So you want to find another x, which is a set. So given a bunch of sets, you want to find another set x, right? Such that the sum of these Jacquard distances to all these given sets is minimized. How do I solve this? This is a surprisingly open research question. And this is very surprising because Jacquard distance is very well used. You talk to Google, they use, maybe we can refer to that, they use this Jacquard distance every day probably. I mean, a million times every day probably in sort of what is known as the clustering of their web pages. However, we cannot solve this very, very simple question in this Jacquard distance, right? In fact, the only previous algorithm that we knew was this guy's by Path, I don't know how to pronounce it, and it says that, okay, if my size of the universe is n, it gives an algorithm that's like 2 to the power square root n to solve this. These guys, Flavio and Ravi Kumar and others, they give a polynomial time algorithm, the first polynomial time algorithm. So imagine how surprising this is. We have known about this distance for over 100 years. We know about the first polynomial time algorithm in 2010. Even that gives an approximate Jacquard distance. I mean, solves this problem approximately. So what does that mean? I don't want to go into this. Basically what it says is that, okay, you can get to within 1% of the optimal, or some 0.1% of the optimal cost of this in some sense. Okay? But this is not, I mean, any of you solve this, you're most welcome to sort of claim a PhD. Okay. So we're done with distance functions for now. Now, next comes the question of defining objective functions, because as we saw, right? I mean, have I convinced you that the question of clustering is nowhere as trivial as it looks, right? You haven't told me, okay, how many clusters do you need? Do you need one cluster? Can I put all points in their individual clusters? Because then there's nothing to do, right? So I could be, the objective function, typically there are different categories. I could be defining the number of clusters. A set of points are here. I could be saying that, okay, cluster this using 2 clusters. Maybe this and this is the optimal clustering. But cluster this only using 2 centers. Or I could be saying that, okay, you can use multiple clusters, but what you have to make sure is that you have to make sure some kind of separation between clusters. Because maybe, I don't know how many clusters are there, right? But what you have to make sure is maybe that each cluster's radius, right? So this is, so intuitively, I'll say what the radius is. So imagine the cluster as a ball, right? Imagine the cluster as a ball, which is, imagine that you take all the points in a cluster, and then you take the maximum pairwise difference between any 2 points in a cluster. That I can define as the diameter of the cluster, and radius may be the half of that. Okay, so you can use however many clusters you want, but you have to make sure that the radius of the clustering, each cluster is small. That's an alternate way of defining a sort of clustering, right? I'm not telling you the number of clusters a priori because I don't know, but I'm telling you that each cluster has to be somewhat tight. Then there are other points about graph-based measures and so on. We'll also see about working without an objective function, right? And this is this will be in the general category of hierarchical clustering schemes, in which we'll try to first define an algorithm and then maybe try to extract an objective function later on, think about an objective function later on. But that's primarily because we don't know much yet. I mean, the theme of this is that we don't know much yet. Sorry, is there any question before I delve into one specific clustering? Any question on this? Yeah. In the cosine distance. Yeah, so the question is that when we look at the cosine distance, we are losing some information, in the sense that we're losing, because we have normalized each vector, we're losing the information that okay, one of them might be very big, another one is very small, and we have lost that in the distance. The point is that sometimes, that's a very good point, the point is that sometimes you want to lose that. Because I'll give you an example, because let's say you're looking at a document, right? And it could be, and let's say you're trying to see if these documents are on the same topic, right? It could be that one document is really, that the 2 documents is really the same, let's say the 2 answers to problems. But one of the people just wants to write more. He's written about the same things, but sort of over and over and over. In that case, right, it makes sense to, let's say, normalize the 2, right? Take the count of words in each of them, and then we normalize the 2, and then we compare the angle between them, right? So see, again, until now what we have covered, right, is mostly art, right? In the sense that we are giving you different kind of tools, right? We are telling you that this is a principled way of thinking about these tools. This is how you should think about distance function. This is how you should think about objective function. Which one you choose is really the art of machine learning, the art of the data science, because that depends on how you understand this particular data set, how you understand this particular problem. There's no guiding principle. All we can tell you is that, okay, if you choose this distance function with this objective, here is what I can do for you, right? Okay. Any other question? But that was a great question. Thank you. Any other question?
Why did the significance of
Huh? Why did the?
significance of Jaccard distance?
Good point. Again, what is the significance of Jaccard distance? Why not look at all the others, right? Because again, sometimes I mean, sometimes things are more naturally representable using sets, right? So there are two kinds of significance. So one of them is that there's a bunch of algorithms. So one of them is purely empirical, because it has been seen that if you cluster things using Jaccard distance, sometimes there are claims that say that this corresponds to a more natural clustering if you show to people. You can also see these kind of papers that this corresponds to more natural clustering. Either when you show it to people or when you apply it in the machine learning pipelines. Because see, at the end of the day, this is really only one part. It's possible that you take this clustering, right? Then you apply it to a supervised pipeline. Then you can create features out of this clustering. Right? So the notion of Jaccard has been important because, number one, we have good algorithms for it, very efficient algorithms for it, for clustering in Jaccard and so on, and for doing things like finding out nearest neighbor. And there's also been, works that say that, okay, if you let's say, this is actually a paper that I'm talking about. There was a Google News personalization paper that said that, okay, they had this problem that, okay, that they curate, Google News is an automatically curated page, right? No human sits down and creates a Google News page, just like people do the New York Times page. So what they do is that they collect all these news feeds from different agencies, and then they will cluster these news to say that, okay, this news and this news are really the same. This news and this news are really the same. So I should put only one copy of them prominently, and other ones may be in small letters, because you don't want to see the entire news page filled out about only one type of news, right? And then there were some results that say that people preferred Jaccard distance-based clustering and so on. Does that answer your question? Anything else? So let's talk about k-means. Okay. So in k-means, here is the problem. So we'll be given a bunch of again objects, okay? And now that we have talked about very specific, very generic things. Now let's come down to when the objects are points in d-dimensional space, points in Rd. Okay. So here d equal to 2, of course. And let's say that we define the distance function to be L2. Right? In the sense that this is only straight line distance. Okay? What is it that we are interested in the k-means? In the k-means, what we are saying is that there are two slightly different formulations, and they are basically the same. What they're saying is that, okay, put down two cluster centers. Right? And then associate every point with the nearest cluster center. For instance, this one goes here, this one goes here, this one, I don't know, tricky to say. Maybe it goes here. Associate every point to the nearest cluster center. Right? This is this mean Cx that you're saying. That for every point x, Cx is closest center to x. Okay? And then you take all these distances from x to Cx, you square them up, and then you sum them up. So basically every point only contributes only once. Okay? And the sum of squares of these green lines that I have drawn. So this is my cost of clustering. This is known as the cost of the clustering. According to C1, C2, Ck. Right? So another way I could be sort of defining this is to say that, okay, the C1, C2, Ck, they naturally partition the input data. Right? In the sense that if you take all the points that are closest to C1, that is one partition, all the points that are closest to C2, that is another partition. Right? Then I'm defining the cost of each partition by the sum of the distances of sum of squares of distances of every point to the center. This is the k-means cost. Okay? Now the question is, find out the cluster centers, or equivalently find out the partitioning, as we'll see that they're equivalent, to minimize the above cost. Very straightforward. Let's say k equal to 2 here. My question was that, where should I put these two green boxes, these two green squares, so that this cost is minimized? I've defined the, see, once I put down the green squares, right, the cost of the clustering is clear, because every point goes to the nearest one, there's no ambiguity on that, and then I sort of define the cost. So then what is the what is the best way of placing this boxes? See, this in some sense is prototypical of the firefighter question, right? As we mentioned that imagine these are the locations of the houses, and where do I place the fire stations? That's what we're asking, right? So that when the sum of these distances is minimized. There's a surprisingly large amount of work on k-means. There's a surprisingly larger gap between theory and practice in k-means. That the algorithms that people sort of have developed in theory have become more and more complicated and sort of better in terms of the approximation. The algorithms that people have been using in practice have more or less remained the same for the last 30 years. Except in the last 5 years or 10 years probably. 5 years probably, when these two have begun to converge, which is why I think it's a really nice sort of question to sort of get started on, to sort of get introduced on, because as you will see that theory and practice, there's this gap, then that sort of, this gap influences a lot of questions in theory. They develop new algorithms, slightly variants of the new algorithms. That influences practice, and then they start to converge, okay? So that's why I really like this. Okay. So here is the way that we were kind of looking at, right? We were kind of saying that okay, we have put one of the centers here at the center of the green ball. We have put another center here at the center of the blue ball. Then we are measuring the distance, right? In some sense, what we are saying is that we are minimizing what is known as the okay. Let us sort of say this. So as I mentioned, that we could be doing two things. I could be saying that okay, you put down the centers, you associate them with the points, then you try to minimize the radius of the clusters, right? That where the radius is defined as the distance of the center to the farthest point in that who gets associated with the center. This could be what we are doing. However, there is a very nice interpretation of k-means that says that, okay, this is not what we're doing, but what we're doing is slightly different, right? What you could say is that okay, we're not doing that. What we're doing is that you take all the points, and you measure all their pairwise differences in a cluster. All the pairwise distances. If there are like m points in a cluster, you measure all the m choose to pairwise distances. Okay? And then you sum up the squares of these distances. And we are claiming that this is really like minimizing the variance in a cluster, right? I'm trying to say that everybody in the cluster should be close to everybody. That is my clustering cost. And we're claiming that this definition of k-means is really the same as my previous definition, where you took the center, and then you measured the distance of everybody with the center, and then you squared them up. Why is that? So here is what we're claiming, that if I do xi minus xj square, ij belongs to cluster C, this is equivalent to modulo some constants, I belongs to cluster C, xi minus C, whereby this C, I mean the cluster center of C. There is a square here. That these two are equivalent. Is it clear? No. Why is it clear? Anybody who knows would have answered me. That these two definitions of k-means are equivalent. This is really algebra, so I won't bore you too much with this. What you can do, then you break this a square plus b square. Then you get the dot product, right? See, a square term corresponds to xi minus c whole square, which is really this term itself. B square term corresponds to c minus xj, which is again really this term, right? Then the mid term is really the dot product of xi minus c and c minus xj, right? And that term I'm claiming is equal to 0. Why? Because c is the center. This term would turn out to be 0. Okay? we can do that. We can do the, so note this down, we'll do this calculation in the tutorial. And so this objective function would be the same as this objective function. Okay? So this is the k-means objective. Is the objective clear? Set down the centers, measure associate everybody with the closest center, take the distance, take the square of the distances, and then take the sum. So now what? How do I optimize this? How do I, given a set of, so what is my input? My input is two things. What is my input to my algorithm? The data points, some L2 represent some representation of data points in the vector in the space, and the number k, and the number k. K has to be given to me. Okay. Now, and I have to return either the clustering or the partitioning of the data points or the set of centers, basically. Let's say that the set of centers. So this is known as Lloyd's algorithm. Okay. So sometimes this is also known as k-means algorithm, but I think that's a little sort of imprecise way of characterizing it, because k-means is really the objective function, but some books tend to refer it also as the k-means algorithm, because really this is really the prototypical algorithm for k-means. Okay, and this is the iterative algorithm, right? So what are we saying? We are saying that okay, start with any location of the centers, right? So the points are somewhere here. Start with the centers. Start with a center here and here, somewhere, right? What is the next step? Next natural step? Find distance, associate everybody to the closest center, right? Associate everybody to the closest center. What is the next natural step? Right. So once we've associated, right, let us try to correct my previous estimate of the center, because my previous estimate of the center was a guess. So the way I correct it was to saying that okay, that these are the points that have been that have kind of come into this cluster. Let us find the mean of these points. Maybe it's this. Then right. Let us find the mean of this point. Maybe it's this. And these are my next guesses at the center. And then I do again the same thing. Right? Then I associate everybody with the new set of centers, right? And then I keep on going. So why do I need to keep on going? Why does it not stop only in one round? Why does it not stop when I choose the set of centers? I associate every point and then I recompute the centers. Why is it not done?
Maybe outliers affecting it.
Maybe?
Outliers maybe influencing it.
Maybe outliers are affecting it. Not really a question of outliers, huh?
Maybe the point is moving into one cluster, another time at other cluster.
Good point. Yeah. So the question is that, let's see, when I recomputed, when the centers moved, right? When the center, I'm just rephrasing the answer. When the centers move, it's possible that a point that was close to C1 before, that was close to the first center, now becomes close to the second center. Right? That's entirely possible, because I don't know what is happening. So in that case, I have to keep on going, because now when I recompute the set of centers, it's again going to change, because my center assignments changed. Right? So therefore, I have to keep on going until I converge. What does converge mean then? What is my convergence criteria? So one possible convergence criteria is that no point changed its center assignment. That's a very natural thing, right? That no point changed its center assignment, and then clearly it's not, the algorithm is not going to proceed anymore. Okay? So that's one way of going for it. Yeah.
Can there be another kind of criteria for conversion?
For?
Can there be another kind of criteria for convergence?
So the question is that can there be another kind of criteria for convergence? So give us examples. Give us examples. Maybe I shouldn't have shown you. So what could be other kinds of practical convergence criteria?
We can have a threshold. We can have a threshold.
You can have a threshold on the set of points that have changed. Potentially, you say that okay, maybe we're never going to reach 0 points changing. Maybe let's say 0.001% of the points change their center assignment, right? That could be potentially much more sort of practical. Anything else? Another convergence criteria that's typically used is when the cluster centers themselves don't shift much, right? That you say that, okay, that these were the original locations of the cluster centers in the previous iteration, right? And you measure where the new cluster centers are located, and then you sort of measure the shift, right? This is not perfect, because it could be that even with a small shift in cluster centers, a bunch of new points change their center assignment. So this is not perfect, okay? However, it's something that works in practice. It works in practice. It has a lot of issues, though. We'll sort of see. Okay. So now this is the algorithm. Yes.
Sort of alternates something, or is it to be converging on?
Good question. We'll come to that. These are all very good questions. So the questions that are being asked is that how do I know that it even converges? That it even stops? Even with any of these criteria, how do I know that it even stops? That this could be, I've really written a while loop, while not done. And the done sort of logic is somewhere inside that says that that's all these complicated things. How do I know that it even stops? Right? I mean, I don't know. We'll have to see. We'll have to look at this, right? So we look at a couple of things. First of all, we'll see that okay, it potentially it converges. It does not sort of, and the way we'll sort of look at this is by saying that okay, it does not repeat the same configuration, it does not come back to the same configuration again. What does that mean? What it says is that suppose you're thinking about k equal to 2. Suppose you have n points. Right? So how many possible clusterings are there? So how many? But number of centroids is infinite. Right? Number of centroids is infinite, right? Because I mean, any point in the plane can be a centroid. So imagine these points are in R2. Doesn't matter. So but how many clusters are there?
There can be infinitely many clusters if we can make. But we are
N? Why n? I'm hearing an answer n. Why n? No, there are only 2 clusters. How many possible clusterings are there? Maybe maybe I sort of rephrase my question. With two clusters, how many possible clusterings of the points are there? Let me rephrase my question. Infinite? Really? Infinite? Votes for infinite? Votes for finite? N square. So n square is one answer that I have to remember to keep on changing. So n square is one answer that we are seeing. Anything else? N square? N is another answer that we are seeing. So infinite is another answer that we have seen. None of these are true. Huh? Okay, to me n and n plus 1 are the same. 2 power n. Okay, so why 2 power n? Right. So 2 power n. Because the clustering is really, so think of it as a partitioning of the data points into either you put them in cluster 1 or in cluster 2. And for every point you can decide whether to put it in cluster 1 or cluster 2. So then there are 2 power n choices. Right? So potentially there are 2 power n clusterings. What we'll see is that k-means visits, when you run k-means, let's say with k equal to 2, each of them will be visited at most once. And therefore, k-means is guaranteed to converge in time 2 power n. Because look at this k-means, look at these possible clusterings. We'll say that k-means visits each of these clusterings only once, not more than once. That is, it won't come back to the same clustering ever in this iteration, which is what your question was. right? In some sense, right? So it is never going to come back to the same clustering config. This is known as a configuration or a clustering, whatever you want to call it. It's never going to come back to the same clustering in a later iteration, right? That means it's going to only take 2 power n. This is not a very great algorithm, right? 2 power n. Who cares about 2 power n? Okay.